Welcome to Chem Time. Friends, welcome to the presentation. Today's presentation is about identifying whether a given system is open or closed and application of first law of thermodynamics accordingly. And this presentation is useful to chemistry students. This presentation is also useful to chemical engineering, mechanical engineering, petroleum engineering, and agriculture engineering students. I start the presentation by highlighting the importance of today, that is June 28th. In the year 1956, on June 28th, the first atomic reactor, whose capacity is 50 kilowatts, that was built for a private industrial research, started its operations in Chicago. Coming to the presentation covers the two concepts. First one is to identify whether a given system is open or closed system based on the given data of a problem, and relate the thermodynamics, the energy balance to heat exchanger. The first problem that is given is, this is given in GATE 2016 for mechanical engineering. Steam at initial enthalpy of 100 kilojoules per kg and inlet velocity of 100 meters per second enters an insulated horizontal nozzle. So the moment it is insulated, we know Q is equal to 0, and once it is set horizontal, the G delta Z term becomes 0. It leaves the nozzle at 200 meters per second. And what is the exit enthalpy? It is given in 2016 mechanical engineering. This is the problem of a open system because there is velocity, there is a flow in the form of velocity. So we have to apply the first law of thermodynamics to an open system, which can be written as delta H plus delta U square by 2 plus G delta Z is equal to Q plus W. Here Q is heat energy per unit mass and Ws is shaft work per unit mass. Delta H is specific enthalpy change, delta U square by 2 is specific change in kinetic energy, G delta Z is specific change in potential energy. The data that is given is inlet enthalpy, specific enthalpy 100 kilojoules per kg, inlet velocity 100 meters per second, the exit velocity 200 meters per second. As we have mentioned, Q is equal to 0, W is equal to 0, and delta Z is equal to 0. With this, the energy balance, the first law of thermodynamics to an open system becomes H2 minus 100 kilojoules per kg plus 200 square minus 100 square by 2 meter square per second square plus 0 is equal to 0 plus 0. Q is 0 and W is also 0. So therefore, H2 minus 100 kilojoules per kg, 15,000 meter square per second square. As we have seen in our previous presentations, the meter square per second square can be expressed in terms of joules per kg. But here the H1 is in terms of kilojoules per kg. So this also will have to be expressed in kilojoules per kg, which boils down to 15. So as a result, the enthalpy at the exit is 100 kilojoules per kg minus 15 kilojoules per kg, which is 85 kilojoules per kg. To the second problem, this is also given in GATE 2016 for mechanical engineering. Work is done on an adiabatic system. The moment it is adiabatic system, Q is equal to 0, due to which the velocity changes from 10 meters per second to 20 meters per second, and elevation increases by 20 meters and the temperature increases by 1 Kelvin. The mass flow rate of the system is 10 kg per second. The specified constant volume is 100 joules per kg Kelvin, and gravitational acceleration is 10 meters per second square. If there is no change in any other component of the energy of the system, the magnitude of the total work on the system is. This is the case of an open system. For open system, the energy balance equation becomes m dot brackets delta H plus delta U square by 2 plus G delta Z bracket closed is equal to Q plus Ws. For adiabatic system, Q is equal to 0. Delta H can be replaced with Cv delta T. So as a result, the above equation becomes m dot brackets Cv delta T plus U2 square minus U1 square by 2 plus G delta Z is equal to Ws. Now, with the values given, Cv is equal to 100 joules per kg Kelvin, delta T is 1 Kelvin, U1 is 10 meters per second, U2 is 20 meters per second, delta Z is 20 meters, m dot is 10 kg per second. As we know, Q is equal to 0. The equation boils down to 10 kg per second brackets 100 joules per kg Kelvin into 1 Kelvin plus 20 square minus 10 square by 2 meter square per second square plus 10 meters per second square into 20 meters is equal to Ws. Ws then becomes 1000 joules per second plus 1500 joules per second plus 2000 joules per second, that is 4500 joules per second, that is 4.5 kilowatts. Coming to the problem that is given in NEET 2019, a gas at 300 Kelvin expands from 0.1 liters to 0.25 liters against an external pressure of 2 bar. The work done by the gas is. Here, the work is done by the gas. As a result, work becomes negative. So, in the given choices, A is 30 joules, B is minus 30 joules, C is 5 kilojoules, D is 25 joules. Straight away we can say the B is the correct option because it is the only negative value in the given values. This can be shown mathematically also based on the work of compression, rather it's a work of expansion in this case. W will be minus integral V1 to V2 P external into dV. P external is external pressure and V1 and V2 are given. V1 is 0.1 liters and V2 is 0.25 liters. So the equation becomes W is equal to minus P external integral V1 to V2 dV. P external is 2 bar, V1 is 0.1 liters, V2 is 0.25 liters. With this, W becomes minus 2 bar 0.1 liter to 0.25 liters into dV. Minus 2 bar brackets 0.25 liters minus 0.1 liters, that is minus 0.3 bar liters. But all of us know 1 bar is equal to 10 power 5 newtons per meter square and 1 liter is 10 power minus 3 meter cube. With this, W becomes minus 3 bar into 10 power 5 newtons per meter square per bar into liter into 10 power minus 3 meter cube per liter. That boils down to minus 30 Newton meter, that is minus 30 joules. Coming to the last problem, the connectivity between heat exchanger and thermodynamics. The first law of thermodynamics for an open system can be applied to a heat exchanger, which is also an open system. A heat exchanger contains cold fluid or fluids, and hot fluid or fluids. The energy balance equation is to be written separately for hot fluid or hot fluids and cold fluid or cold fluids. Combining the hot fluid energy balance with that of cold fluid energy balance gives the overall energy balance of an open system of heat exchanger. So the general balance energy balance equation is m dot into delta H plus delta U square by 2 plus G delta Z is equal to Q plus Ws. Now, since there is no change in potential energy because most of the heat exchangers will be placed horizontally and there is no change in velocity of the fluid either on the shell side or on the tube side and there is no shaft work, the energy balance equation gets simplified to m dot delta H is equal to Q. Q is the amount of heat gained or lost. So equation 2, the simplified energy balance, will have to be used for hot fluid as well as cold fluid and then it has to be combined. If the hot fluid loses heat at a rate of Q1 and flowing at a mass flow rate of m1 dot with inlet and outlet temperatures of T1 and T2, the energy balance for the hot fluid becomes m1 dot into Cph into T2 minus T1 is equal to Q1. Cph is the specific heat of hot fluid. On similar grounds, the energy balance for the cold fluid becomes m2 dot into Cpc into T2 minus T1 is equal to Q2, where Cpc is specific heat of cold fluid, m2 dot is mass flow rate of the cold fluid. So combining the overall energy balance then for the hot fluid as well as the cold fluid, or whatever the heat that is lost by hot fluid has to be gained by cold fluid for an adiabatic system. So Q1 plus Q2 is equal to 0. That is M2 dot into CPC into T2 minus T1 plus M1 dot into CPH into T2 minus T1 is equal to 0, which becomes M2 dot into CPC into T2 minus T1 is equal to M1 dot into CPH into T1 minus T2. And this is the energy balance equation we use in case of a heat exchanger. With this, I conclude my presentation. Thank you. Request you to like, share and subscribe my channel.